Hello everybody, I am Arya More, a final year student at COP School of Metallurgy and Material Sciences. Today I'll be talking about a project I did this summer, which was constructing a diffusion couple made out of pure titanium and an alloy of 90 atomic weight percent titanium and the rest Fe. The first step was melting the raw materials which I talked about in an induction arc melting. The induction arc melting furnace was used to protect the samples or the specimen from the open atmosphere and to maintain the cleanliness and homogeneity of the specimen. The temperature in the induction arc furnace was around 3000 degrees Celsius and a pressure of 10 to minus 6 mmHg was maintained. The next step in the experiment was the homogenization of the samples, which was heating the samples at 1000 degrees Celsius for over a period of 4 days. These are the microstructures which we revealed after cold mounting and polishing up to 2000 ml grade paper. There was no issue with the pure titanium structure as it was a complete single alpha phase, but there was an issue with the iron titanium alloy. As we can see, there are needles in the microstructure which suggest that the specimen might be brittle. But we were allowed to continue with the next step, which was the crystal polishing. Crystal polishing was done in order to ensure that the samples were flat. The next step was using the alumina markers. We placed a small quantity of alumina along with ethanol on the sample, and then this mixture or slurry was allowed to evaporate. Remaining was the alumina markers which were placed on the sample. Then the diffusion couple was placed into a jig which was made up of stainless steel, and the jig was placed into a diffusion heat treatment for a whole day at 1200 degrees Celsius. Next is the APMA analysis, which I am going to talk about. These are the results for the APMA analysis. This is a pretty easy graph to understand. There is atomic weight percentage on the y-axis and displacement on the x-axis. As we can see, the quantity or the value of titanium increases as we move from left to right, and the quantity of iron decreases as we move from left to right. This suggests that the iron atoms move into the titanium rich region, and the Ti atoms move into the Fe rich region. This is nothing but the Kirkendall effect, which I studied during my structural metallurgy course. What followed was the metanoplane analysis. Metanoplane is the plane at which the atoms that move into the left side are equal to the atoms that move into the right side. The first equation basically says that the moment of a concentration profile around the metanoplane or the metano interface is 0. Here, in order to convert a partial differential equation into an ordinary differential equation, a new parameter which is eta which is equal to x by root t is introduced. The third form is the more intuitive or the alternative form of the first equation, which suggests that on the left side there is a gain of the component B from Cb minus to Cb, and on the right side there is a loss of component B from Cb plus to Cb. These are the results of the metanoplane analysis, and the metanoplane is found at x is equal to 1 millimeter. Now this is the final part of the experiment, where we have plotted the interdiffusion coefficient versus the Fe concentration, and at the 95th percentile the value of D is 1.75 into 10 raised to minus 10 meters square per second, which lies in the range of the literature review values. And through this course I learned in detail about the physical metallurgy of non-ferrous alloys, the structural metallurgy and heat treatment as well. I also studied fixed diffusion laws, about fixed diffusions law and Kirkendall effect in general, and that was about it. Thank you.